Giorgio lecture on Scalar products and suspect.
Thanks. So this is the title that you know, and today I will apply the setting of distance that I studied yesterday. So when I say V vector space and Q a quadratic form, this is Euclidean space. One of the main examples I have in mind, of course, is when V is a tensor space, which is exactly in the spirit of this meeting. But anyway, it's better from the very beginning to start in generality. So this is just any Euclidean space. And then consider a subset X. What is the distance function from a point to X? Just you compute the Euclidean distance at any point, and you minimize when you can, and when it is closed, the subset you always can. So there is a minimum, can be not unique, of course, but there is at least one minimum by obvious analytic reasons. And when you have an extreme of the function, we have a critical point of the distance function. So critical point means that now we will see geometrically, but essentially that the gradient, when it is differentiable, it vanishes. There is some, now I don't care here, but there is some result in analysis which shows that the minimum is unique if and only if the function is differentiable there. And since the distance is Lipschitz, by Rademacher theorem, it is differentiable almost everywhere. So what I'm doing has a sense, I mean, even in a general analytic setting, but then for most of my talk, X will be algebraic. And then also here I underline the fact I told yesterday that when I computed the minimum and maximum, I could just, square here. Anyway, remove the square root and comes just an algebraic function. So let's do geometrically. This is the picture. You start from U, you compute the distance from X, and here the minimum is one of the critical points that are attained. You see, when I told before, the distance has the gradient which vanish, and geometrically means that the tangent space to X in this point is orthogonal to the segment we join U with X. So, okay, here is the formula. Orthogonality between these two things. Now there is a warning, of course, that there are many software that compute the distance just working locally. Oh, there is a question.
Maybe I just missed it, but could you repeat what a critical point is? It's a point where the minimum is attained in the description, or
a critical point is defined by this way.
Oh,
okay, so but it's equivalent to say that the distance function has a critical point as a function, so the gradient vanishes. As a function on X, so you fix U is a function on X, and you are saying that the minimum vanishes there. But your question, of course, is meaningful, that when you have such a critical point could be a maximum, a minimum, or a saddle. No, it can be just the usual analytical pattern. And there are software which compute the minimum locally. So you start from some point and you converge. But of course, you have never the guarantee that what you compute here is only a local minimum, because here could be coming again closer and you are not looking here. So a possibility to be sure, to guarantee, to testify, to certify that what you found is really a minimum is compute all critical points. And for general U, there are finitely many. So if you compute all critical points, you just compute the distance at each of them, and you can check the minimum if it is unique or not, and depending on how many you have. So this will be important in the following, and I anticipate that the number of critical points in some sense measure the complexity to compute this minimum. Okay. Let's go ahead and
so it quantifies the complexity of computing global minimum.
Compute globally the mean. That's correct. Yes. Something happened. Maybe. Sorry.
No, it's just pressed on.
No, I think just the battery. Okay. So this study is very classical. You know, there is a paper by Apollonius in the Hellenistic period of Greece. There are, I think, maybe 9 books about conics. And already there, it's quite interesting. He posed the problem to study the normal line to an ellipse, so exactly the critical points of the distance. And he finds these cases. For example, here you have an ellipse. You have 2 normal lines. Here you have another point. You have 4 normal lines. And this is the maximum. Nowadays, we can say there is an algebraic equation, and the number of complex lines is always 4. And when there are 2, the other 2 are complex conjugate. So you don't see, but there are on the complex numbers. So the equation which gives the normal lines for us has degree 4. And 4 is the complexity in some sense to make this computation. And it's quite astonishing that this approach was already taken 3 centuries before Christ. And nowadays we can also, I will show you now an interesting animation. What's the probability to get 4? What's the probability to get 2? No, yesterday I gave you the probability to get the real roots of an equation, so you can apply to this particular equation. And if you take the Gaussian, well, the answer is quite equanimous, 3, 0, 4. There is a slight preference with 4, but that's the average number of normal lines. And now I show you, I hope it works. In Wikipedia, there is this picture that computes all the normal lines to an ellipse. And let's see if I... No, it does not work. So, okay, if you want, you can enjoy and go to Evolute in English page of Wikipedia, and there is this animation, and all these are normal, and there is an envelope, which is a sextic curve. I will show you later the equation. Sometimes it's called an astroid, sometimes it's called Lamé sextic. Here in Nice, I prefer to call Lamé, of course. And what is going on is that the number of the real normals is 4 inside and 2 outside. Why? Because when the number changes between 2 and 4, it means that the two solutions collide, and then you have a multiplicity. Then you are like just in the envelope, because infinitesimally, 2 normal are just collapsing. And then this curve is the boundary between the region when you have 2 inside, when you have a 4 inside, and the region when you have 2 outside. That's quite beautiful, and I recommend in my undergraduate class, I do Grabner basis, and this is one of the favorite examples that the students enjoy. And it's a basic problem, and compute this equation without a computer is quite difficult. And with the computer nowadays, it's just one example in elimination theory. So it's a beautiful example. Okay.
How do you call the object that is traced?
Maybe I did not tell the name. It's called evolute. So for any curve, the evolute is the envelope of the normal. This is one definition. In the book, maybe you find another definition which is equivalent. For every curve, you compute the osculating circle, and the locus of the center of osculating circle is the evolute. They are equivalent. It's easy. It's an exercise to prove. And in Wikipedia, it's really well done. And there is also the equivalent show. There is the ellipse with all the osculating circle drawn in animation, and you see the evolute there. It's quite, let's say, a bit counterintuitive, because the point here, the center of the circle tangent here, and conversely. So they go up and down. It's quite beautiful. Okay. Now, there is a thing in application in what is called computer-aided geometric design, when use this fact, and they are called the offset. Essentially, it's the same thing as before, but now explain. Offset curve of x are the curve which have a given distance fixed. So now you start from the black curve, and you fix a number, maybe epsilon, and the offset is 1 here and 1 here. I love these things by chance. One of my closest friends is a mechanical engineer. And 30 years ago, he had this machine when I had to model the black curve, and the machine was a sphere. And of course, they had in the software to say to the machine that to put the center of the tool quite close, exactly in the radius. So if you want to model the black, you have to put the radius here. So it's quite important to have these things. And algebraically, it's interesting that if you start from the black curve, you fix a radius, you always find it as offset for such a radius a couple of curves, and you can think it is reducible. There are one inner, one outward, but of course that's not true. The Zariski closure of the inner contains both. And so in algebraic geometry, you know, like when you have 2 branches of an hyperbola, this is also, if you ask, this is Zariski closed? No, this is Zariski closed. They come together, and the same happens here. And now, you can ask if this black curve has some degree, what is the degree of the red? It turns out it's exactly the same problem as before. You have to count how many normals do you have from a general point, and then the degree is twice this number. That's quite interesting. So the measure of complexity I told before now can be measured. The degree of the offset is in some sense the measure of complexity, which is in application, of course, correct. For example, here I show the sinus curve and the offset of the sinus curve. I draw only one part, and you see it's interesting because they are smooth only for a while and then they become singular. Okay, now as a mathematician, usually when you have a problem, you try to start from the most trivial case and see what happens. The only two cases which are completely trivial are affine, and then another I will show in a while. Start from affine. Well, for any affine space, it's obvious that the offset is given by two affine right and left in the same distance. So for example, 2 green and 2 red. And also it's obvious that if you want to compute the distance from one point, well, there is a unique solution, the orthogonal projection. And there is this analogy. These are the only varieties which have only one critical point, the affine subspace. Then there is a second trivial, the sphere. This is two-dimensional picture that can be done in any dimension. If you start from the black curve, which is a circle, the offset is a pair of circles. And in this case, the variety is really reducible. So the two circles, each of them, of course, is risky closed. But it's a coincidence of, I did not notice, but also before. If you increase the degree, and if you go for the ellipse, for example, is no more two. You cannot separate the two curves.
So it's not the degree. Ellipse is also.
Sorry?
Ellipse is also degree 2. You said if you increase the degree.
You're right. If you increase the complexity. Yeah, thanks. You see, it is a metric problem because circle and ellipse behave differently, even if they have the same degree. Now, what is the Euclidean distance polynomial? You start from x, one of the black curve before. You start from a variable u, and this is a polynomial in t square, which defines the offset hypersurface of all the points u such that the distance is t. So algebraically, you pose the square distance equal to t square. This square means that you have inward and outward as before. Now the degree of this polynomial computes the number of complex critical points and has a name. It's called the Euclidean distance degree. And I want to show and introduce this fact. We studied this in a paper with 5 authors. I am one of the 5, Jan Drijsma, Emil Horvath, Bernd Sturfus, who was in some sense the boss of the group, and Rekha Thomas.
You're in the center.
Yeah, by chance. You know that in the outside of mathematics, the important authors are the first and the last. So the center is the minimum. Okay. Now I show you this computation, which is nice, that you can find in this beautiful book, Salmon Cayley. The name is Plain Algebraic Curves. Maybe exists a PDF online, luckily. And they compute what we call ED polynomial of a conic. How? They do this nice argument. Take two conics. Then this is a geometrical proposition. When two conics are not tangent, so means they have a transverse intersection. So let's make a drawing. Here the intersection is transverse, and here not. You have tangency. And how you can detect this fact? So is equivalent to say that the intersection is given by 4 distinct points, and this is obvious. But what is not obvious is an algebraic way to consider the pencil, and when they are transversal, this pencil has exactly 3 distinct singular conics, and you see this is well known. This is one. Then I can change. This is 2, and then you have a third one. I don't go just changing the pair of points. So the discriminant of the cubic equation, which gives the determinant, is the invariant that check when two conics are transversal. That's nice. And the proof is not difficult, but it's also non-trivial. One direction you have to fight a bit. And then, okay, this is indeed the proof, but I prefer to skip. Then you can use this to compute the polynomial and the offset of the ellipse, because you start from a circle. You can think this in this way. You have here U1, U2, and a radius t, and you want to understand when you are tangent to a given conic. So you pick E, your favorite conic, B, such thing. You take the pencil, you compute the determinant, and then by the previous proposition, you get the condition of tangency. So the center, which is U1 or 2, give exactly the offset. It's a smart idea, which works perfectly, and gives the following interesting result, that for the circle, the degree is 2, so you have just 2 normals. Maybe I told you, but I don't show it's trivial, but this is U. The normal is the same, but you have 2 critical points. And for the parabola, you get 3. And all other smooth conics, you get 4. So it gives, in some sense, a metric complexity of the conics. And you see the simplest one, of course, is the circle. Then you can repeat everything in the projective case. How you do in the projective case? Well, every curve in the plane has just an affine cone in A3, which looks like in this way. And then by definition, you consider the distance of a point, choosing a representative here from the affine cone and the affine distance. The computation are similar, but not exactly equal. And the result is that the ED degree of the projective conic in general is again 4, but now you have a matrix of the conic, and the degree drops exactly when it has multiple eigenvalues. And this means that you have such a particular conic that you can draw, and the result is slightly different. For example, the equilateral hyperbola here has ED degree 2 when you projectivize. But let's show here the difference between parabola and ellipse in the affine case, which I think is nice. This is related to JM when he told me the degree of the parabola and ellipse is always 2. What is changing is the degree of the offset. So here, you start from a parabola and you get the offset. Essentially, the degree is 3 plus 3, and you get 6. These are sexy curves. With the ellipse, the degree is 4 plus 4, so you get octic. So the complexity here is bigger than there. And you can understand if you have already such a mess for such a simple curves, what could happen in general. It is a really fascinating object, and a lot of things are still completely unknown. Then I mention effect which is interesting, that locally distance can be added in the sense that if the distance between red and green is epsilon 1 and green and black is epsilon 2, then the distance between the first and the second is just the sum. And then this gives an equation that you can use if you start from x and you find x at t0 some radius t0, then you can compute again the distance to x t0, and you get this formula, which can be helpful to understand the situation. And here I show the graphic of the distance from an ellipse looked as a surface over the plane. Now you get a sombrero. This is the maximum distance inside, and then you see it is 0 if and only if it is on the ellipse, which is hidden somewhere. And the level curves, if you cut the sombrero with some horizontal, are optics plane. And the ED degree is 4, which is just 1/2 of these. Now, result for a general algebraic curve of degree D, you get a similar picture, and the level curves have degree 2D square. So you can say ED degree is D square. Now the first result, there is a duality. To state the duality, I have to recall what the dual variety is. And now there is a warning. Usually in projective geometry, we have a variety X in a space, and we define the dual variety in another space, in the dual space. So they live in different space. But remember, we have a metric. So the dual space can be identified with our space, and then you can see the dual variety inside the same space. And I give a definition which is a bit not orthodox for algebraic geometry, using orthogonality. The definition is the following.
Just to be sure, if we're working over complex numbers, you're dealing with a symmetric quadratic form.
Yeah.
So it's not metric, but yeah.
It's a metric on the real.
Okay.
It's a metric on the real, yeah. In some sense, my problem is real, and I use the complex just to have extended solution.
Okay.
Yeah. So you start from a cone, and the dual, be careful, is the union of the normal to the tangent space. Okay? This has to be defined in for cones, so maybe let's do a picture, which is otherwise looks confusing. So if I want the dual of this is a cone. Then for each point of the cone, you take the normal. And you make the union of that. And this gives a different cone. Sorry, I'm stupid. I'm completely stupid. The drawing was wrong. This normal has to be computed here. So let's change it. You're rotating, no? And then you have the tangent space rotating, and the normal, you see, they do such a. So that's the dual, and you get a dual cone. You get a dual cone in this way.
So you take
This is the dual.
translate it.
Exactly. I translate into the origin of the normal. Well, I not translate. I just consider here as vector subspaces. Here is the union, and this so is again a cone. And this is a nice way. Is the exactly what is called the dual in convex theory. No, there is a notion of dual convex cone, and it is exactly this one. And that's the dual. And the theorem, if you start of a conic with matrix A, you compute what is the dual, you get the inverse matrix. So in particular, the dual of the dual is the variety itself. This is called the biduality theorem. What's the difference is my definition is that X and X dual live in the same space. That's I want to show. And let's give you the basic example in algebraic geometry. What's the dual of the Segre of two factors? You consider they live in a space of matrices n+1 times n+1. The dual of rank 1 is co-rank 1. So that's interesting. When the matrix is square, it is an hypersurface, which is exactly the determinant. Otherwise, this dual has a higher codimension. So it is just for rectangular matrices, the locus of matrices of co-rank 1 has codimension given by the difference of this number +1. It's interesting because you see, gives a definition of determinant completely geometrical. So you can know anything about linear algebra, you just know geometry and you know the Segre, and here you define an hypersurface, and its equation is exactly the determinant. So it gives a geometrical interpretation of the determinant, which is quite interesting. Second is the generalization of these two tensors. instead of 2 factor, repeat for any number of factor. Here I draw 3, just to make an example. And the dual has a name, it's called the hyperdeterminant. And again, here was codimension 1 when it is square. Here is codimension 1 if and only if the triangle inequality is satisfied. And this is general. The largest has to be smaller or equal than the sum of the other. And this condition, when they are 2, is exactly square. So there is a continuous way of seeing it. And maybe the well-known example is what happens in binary case. This is called the quantum space of it's called a qubit with the 3 modes. The dual is a hypersurface of degree 4. And again, this was studied by Kyrie. And maybe himself he called hyperdepth. And is one of the few cases that you can write down explicitly the equation of hyperdepth is about maybe 16 summas or so. Usually, the equation of hyperdeterminant are gigantic and very difficult to be computed. There is no a Gaussian elimination theory like here that allow to compute the determinant in polynomial complexity easily. The computation of hyperdeterminant is very hard. And that's third case, which is the symmetrization. What happens in the case of polynomials? So when you have the Veronese variety, what's the dual? The dual is called again discriminant, but has a nice interpretation. They are just the hypersurface which are singular, so which contain a singular point. And this is the degree. It's a classical formula found by Bull. And in the case d equals 2, you see this formula drops and it's just the determinant. It's the same because it means a quadratic. But for degree bigger, you see it grows exponentially. So with n, and it's quite high, and again, it's quite complicated to be computed. But all these have in common just to be computed with this stupid geometric meaning of duality. Well, now I want to apply this result to the polynomial. This is the duality. X and X dual share the same ED polynomial, just with the translation. Now we will explain what this means. But there is a funny, and at the same time worrying consequence that if you know the ED polynomial of X, it's just a matter of translation that you can compute the equation of the dual. Why it is worrying? Because I told you before that the equation of the dual is very difficult to compute. So when we saw this, should be some mistake. And what is the explanation? That it is even more difficult to compute the poly. So in some sense, we moved the complication to another object because these use explicitly Grabner basis and elimination, and it starts to be computed. Anyway, theoretically, the consequence is that X and X dual share the same complexity when you want to compute the distance.
So if I take U to be an isotropic,
yes, they still are the same.
yeah, but it's like minus t squared. One is evaluating at t squared, the other at minus.
indeed, for isotropic desimplify, yes, yes. I don't think it's a remark, but still the complication remains. Let's show you the, okay, then the hidden degree is the same, x and x dual share the same. And let's now try to show you the picture from a figure. And this is quite important. The yoga is the following. If x is a critical point for D at the point U, then the difference U minus x that came before is a critical point for the dual. And let's show the figure. Now, my variety x now is drawn red. And this is the dual, the black. In this case, it is just the orthogonal. So you see, if you have a point U, you have two critical points from the red, blue and green. And what is U minus x? You just take the difference. So the green one goes here and the blue one goes there. Just given the operation of making the difference, x, U minus x, x, U minus x. And this is completely formal and can be repeated for any variety, and makes quite I mean, not expected at the beginning relation, and the number QU minus the square that come in the theorem just comes because is the square length of this by Pythagorean theorem, because these two are orthogonal, and then you have this plus the other. Okay. Now this is the Macaulay 2 or any other symbolic like singular or cocoa pattern to compute a dipoly. I don't enter into the details, but there are two warnings. First, when the variety is singular, you have to saturate the singularity. Otherwise, in the singularity, the gradient always vanishes, so you have to remove these points. Essentially, here you are computing the critical points only outside from the singular locus. And then the second warning is the last step. You construct an ideal. You see there are C plus 1 minus of that. And this means that U minus x to be orthogonal to the tangent space has just to be proportional to the Jacobian. This is equivalent. You construct the idea, you have to eliminate the variable x in your ideal U, plus this, of course, formula. And this is the expensive part, and usually it's not feasible. So if you take your favorite variety in many variables, you maybe compute up to here and then you go out of memory, just as a warning. But luckily in small cases, for example, for curves in three-dimensional space, this works perfectly and can give you all the equations. Okay, so after all of this, I can show you a specific example of a conic that was the same that was drawn before. So you see the, if I'm not mistaken, the radio, the two semi-axes should be 1 and 2 if you divide. No, maybe, yeah, okay, maybe 1/2 and 1, but is similar to 1 and 2. And you compute the polynomial should have degree 4 in t square. And indeed, you see there is a monic term T8 come from then there is the term in T6, a term in T4, T square, and this is the term constant. You see, this is the variety that gives zero distance. So t equals 0 is a root here. There is another term that at the beginning is a bit of surprise. This term has no solution over the real, but on the complex number appear, and I will show you later what does it mean. And now, given x, y, z, you get 4 roots in t square, and the minimum positive value is the distance from x. Now enjoy to substitute instead of t square this translation, and it is algebraic substitution because it's a polynomial in t square. And then you get a new equation, and what is nice is that you have the same term here, and in the constant term in red you get the dual ellipse. The dual ellipse, remember, was constructed by the inverse classically. So in principle, this gives a way to compute also the dual variety, but it gives more because it computes the equation. And another thing, for a fixed t, these are just the equation which give the offset that we had before.
Sorry, why is the x squared plus y squared plus c squared plus q of it? How? What's? Oh, I see. That's
This is the u of u. U is now x, y, z.
I got it now.
Okay. Now you take the polynomial as before, you compute the discriminant of that polynomial, and you get this equation. That's not the simplest way, but you get a geometrical information of your curve. You get the evolute. I remember before in my Apollonius drawing, I started with the ellipse, and there was this evolute. I told you this is a Lamé sextic. This is the equation. And this you can find in Salmon Cayley, which is impressive because they have no computer to do this. For example, let me tell that for maybe 1 year I computed this and showed to the students without understanding that there was just a cube minus 4. So this was already noted by Cayley, and it is quite impressive.
So these factors, x squared, y squared, indicate that you have, when critical distances, right, become repeated, but you still have, if you are not on the lemma sextic, you are still not on the discriminant, right? The distances, which are the roots of the degree polynomial, become repeated.
Well, but why 27 and why? Well,
no. X, but in the fact,
this. Oh, you are anticipating what I wanted to tell you. That there are 2 extra factors. No, in my interpretation, these are important because are axes of symmetry. So if you start from a curve and you don't know the axis of symmetry, magically they come from this equation. they correspond, of course, to the singularity here of the evolute, but when you have a symmetry here and here, if you start from a point and the symmetry axis, it means that left and right collapse here, and the four critical points are just two here and two here in the vertices of the ellipse, and the same here. And so there is again a multiplicity, and
but you have four distinct critical points.
yeah. But what I mean is that they are in some sense information beyond the level, which
This count for critical distance.
in my opinion, here there is still a lot of work to be done. So understanding for any curve, computing the discriminant of the ED polynomial, Emil Horobet did this a lot of attempts and always found power 3. But we have not an explanation of the theory, why we get the power 3.
Sorry,
And,
are you using something basic? So what's the geometric interpretation of this hypersurface you get from the ED polynomial?
means that two values of the distance are the same, because you are computed the discriminant of the equation which compute all the critical
Not the
values.
discriminant of it. I'm just saying the ED polynomial itself defines a hypersurface.
Yeah, the point from where, so the point xyz such that if you compute, you have a multiplicity. They could be, if you have an axis of symmetry, certainly you have the same, no? Everything on the left is also on the right, and so. So let me rephrase it differently. In L, these two different distances are in the same point. In X and Y, they could be different points. Indeed, maybe here I did not show you another phenomena that if you start from here, you can have an orthogonal, let's see, here and another orthogonal there, I think. Here probably are not real, but in this case you see. And the distance is the same, I think. So again, it should be part of the discriminant.
Let me just try one more time. So we start with a plane curve, and from that we get three additional plane curves. We get the dual curve, we get the zero set of the ED polynomial, and we get the zero set of the discriminant of the ED polynomial.
Yes, one is contained in the other, but you see from this example,
Question: what's the containment?
the containment is that the evolute, which is the envelope of the normal, divides the discriminant. You see, divided even more with the discriminant, but I don't know why. I can prove only that it divides, but why divides with power 3, I don't know. Okay, your question was here. So maybe what noticed that the ED discriminant is the generalization of the evolute to any variable. And here there is the picture. The ED discriminant of the black is both green and red. Now, there is a formula computing ED degree in this assumption. If X is transversal to Q, what is Q? Q is the isotropic quadric. So the locus when the length of the vector is 0. Of course, you have to compute on complex numbers. This has to be a smooth projective. On the real numbers, you never see such a thing. So if you give the shape of x is not clear what happens. But for example, for a circle and for a parabola, this transversality fails. Because the formula depends only on Chern classes. And circle, parabola, ellipse have the same Chern classes, but the transversality is true only for the ellipse. And then this nice formula compute the ED. You see there is alternating sum with an exponential, and the proof is obtained by vector bundle techniques. And this is projective. When x is affine, you have to compute on the cone, but still the formula is true. But you have to add the transversality with both the hyperplane at infinity and the quadric at infinity. And this explains exactly what I was telling you about circle, parabola, and general conic, which gives a different behavior. Now you understand why yesterday I was so pedantic in that showing if the quadric changes and then the invariance can change and the geometrical situation change. And here we have a clear application that when the quadric changes, this number can be different and changes. So ED degree depends on the metric you have.
Is it even, I mean, a posteriori is, we know it has to be non-negative, but this formula is not clear that.
It's non-clear, but yeah, it is an inequality at the end. It's correct, yes. Good remark.
The transversality is not satisfied, then you have an inequality.
Well, yes, this sum is bigger of potential. That's the inequality.
For the EDW. Can you bound it? Or it's
always.
On the other sense, I'm not so sure.
Same for any cube.
Yeah, maybe
this is an upper bound.
an upper bound.
This is also the same thing you agree.
Any Q.
For any cube, this is
This okay. This is an upper bound, but no, I believe that you were thinking about a thing that depends in. No, okay, this depends on the degree of Chern classes. So can be only smaller of this. Yes.
Okay.
Yeah, that's. But also, of course, is non-negative.
and it's not known, right? That if for a certain cube you have equality, then this implies transversality. This is not.
Should be nice, but I've never seen the proof. Do you know? No. Yeah, Katzgali has a preprint, not a preprint, in a chapter paper. Not yet. Okay, but they want to understand when it is minimum, and the conjecture is that it is minimum if and only if Q is invariant, at least in tensor spaces. And it's tantalizing conjecture. I believe in it. Also has some partial result. Well, now I have to make some choices. There are generalization to the singular case instead of the Chern classes. You take a Chern matter classes, but now it's a bit tricky and should deserve one seminar only for these. Maybe I will put here in the slides. You have to understand the Nash blow up, and it's quite a tricky part. Let's go in a more basic case. Compute everything for matrices. Here is very explicit. If you have rectangular matrices, ED polynomial can be computed, and it is this one. You see, this becomes a square, even if A is rectangular. And what is this? It computes exactly the singular values of A. And this becomes symmetric, so always real, which is the only case I know when all the roots are real. So there are a relation with SVD, with the spectral theorem are quite interesting. This is true for core-rank 1 matrices. It has this easy form, but almost the same is in the case of rank 1. But, sorry, I did not tell the important thing. This formula is pretty nice with Bombieri Weil. So with this metric, if you change the metric, I will show you happens a complete disaster. And again, now when the matrix is symmetric, I think this is a phenomena essentially as the same for the circle, that the offset splits and that this determinant splits. You see, this is a factor in 2. And you can consider just inner and outward in some sense. And it's a nice formula. So I have my own interpretation of why. So what does it mean? That I mean the rank 1 matrices or also the determinant for invariant metric is the closest possible to a sphere. So in the sense, you recall, if you give an ellipse, make the following. Instead of changing the metric, you can fix a Euclidean metric and change in the curve. It's the same, no? And the most beautiful form is a circle, and this gives the minimum. So again, here you have this variety of rank 1 matrices. You fix the Bombieri Weil, and the shape of this if you change projective transformation, is the one that you see it as the closest possible to a sphere, because it gives a very, very small Euclidean distance degree. It is just the minimum on these two, and for square ones is just n. Maybe I show you. Okay, indeed, I had the pointer that in slide 27 we have this phenomena. So the ED degree here, what is this variety? Are just rank 1 matrices symmetric. ED degree is n with respect to Bombieri Weil. Now compute for a general quadric another metric. How many critical points you have? You can compute with the Catanese trifold, because this now applies, and this is the answer. You see, it's incredibly high, it's exponential. So 3 power n minus 1 divided by 2. So this means that really changing the metric is a disaster. So rephrased in another way, if to the students teach to compute eigenvalues, eigenvector, not with respect to Bombieri Weil, but with the general metric, they get much more higher complexity and this equation. This, I think, it's worth to be known philosophically that this is the minimum, and in the paper by Kazgali, they prove that this is the minimum. So it's obtained if and only if you get the Bombieri-Weil or the other invariant. Is correct, no? Is
Well, not if and only.
not if and only. Oh, that's
Cannot be smaller. Cannot be smaller.
so in principle could exist other metrics with the same. It is not yet proved. Another interesting question. Okay. Now, for matrices can be done more. As you know, not only the distance to rank 1, but the distance to rank k, what is called the best rank k approximation. So this means that we keep the secant varieties, not only rank 1, but rank R. You have a matrix here, and you want to compute the critical points here. And Eckert-Young solved this problem. How you compute the critical points? You compute SVD, and SVD has n summons, and usually we see the summand as element in the diagonal, no? And you pick all k of them. And if you order that from the biggest to the smaller, among the k of them, the minimum is obtained taking exactly the first k in order, 1, 2, 3, up to k. It's a very beautiful theorem, and indeed, let's explain a bit more. This variety is closed, so for matrices, border rank is equal to rank, and all the other critical points are obtained by any subset of k numbers among n, and so the ED degree is just this binomial, n choose k. This is the ED degree of the variety of matrices of bounded rank by k, so they are quite mild, you see, they're not show that these things can be computed in a reasonable time.
Well, it is n over 2. Large.
But it's polynomial in n, is not exponential. Before I had exponential, you remember, is that's much worse, I think. Okay, you say when it is exactly n choose n2, is there is a stealing and the still. Okay, maybe.
Exponential.
But at least for small rank, which is usually known for application, this is mild.
But what's n over 2?
For rank 2 is a square, so it's a reasonable complexity. And I also notice that these numbers respect the theorem about duality. Okay, now let me go a bit. I am always optimistic on the time. There is a result that works on any tensor space. You can define in this situation, you have a tensor in the tensor space when you have a group acting. You can define the orthogonal to the tangent space of the orbit. Now, Lig is the tangent. Let's make a picture. You have F as a tensor. You have the orbit GF, and you take the tangent of this, and now the normal. This is called HF. Exercise for a matrix, what is the critical is given by the B such that both are symmetric. So the note it's a linear equation in A. And the theorem, in collaboration with Jan Drijsma and Alicia Tocino, all the critical points of this lie in this subspace. And moreover, the critical points span the critical space exactly if the triangle inequality is satisfied, which means that the hyperdeterminant is an hypersurface, and so it is an equation. Okay, next slide, a classical theorem by Banach. You know that maybe 3 years after he died in concentration camp, he was a Jew. And the theorem is the following, that if you start from a symmetric tensor, the closest rank 1 tensor among possibly non-symmetric one may be chosen symmetric. Maybe chosen means that there could be other at the same distance. This may happen, but anyway, you don't lose anything proving this for choosing the minimum only among the symmetric ones. I think there is a stronger form that all the critical points which are symmetric are also critical point for the set. Of course, there are other critical points beyond the symmetric ones. It's a non-trivial result. And now you want to interpret these critical points for the tensor. And there is this theory which is pretty elegant, that I do now the Segre case, so the tensor without symmetric powers. You will start from F, correspond to T, which is T, sorry, I said stupid. T is a tensor. Ft is the distance function. The critical point of the distance function satisfy these equations. These are analog to singular pair of matrices. So maybe let's show. When so if A is a matrix, also rectangular one, you say a pair xy is a singular pair when A x is equal lambda y and y A is equal to lambda x. Maybe there is a transpose. Yeah? So essentially, contracting with one, you get the other. And here, what is the analogy? That if you contract with all, unless one, you get the remaining one. This is the meaning. So it's exactly a generalization of this. So it is known, these are the critical points for matrices. The theorem by Li Kang, Lim, and Li Kun-chi, they proved independently at the distance of months, and there are 2 published papers. These are exactly the critical points, and you can call singular dupoles. And Li Kun-chi published a book on that you can call spectral theory of tensors, understanding these. And now the question was, how many critical points you have? So what's the degree of the Segre variety? And we got this formula with Shmuel Friedland. The number of singular tuples has a generating function. So you write down this function and you compute the coefficient of some monomial here. Maybe the important thing is how we proved that this is the Chern class of a certain vector band. And the critical points were interpreted as critical point as zero loci of a section of a vector bundle. And let me say a few things. In the binary case, this formula simplified is just the factorial. And there is a generalization to the Segre Veronese when appeared also the multiplicity. Maybe now I skip because I have not enough time. Anyway, this number has some interesting behavior. This is the bundle I told you is a pullback of quotient bundle with simplicity. And then you can understand there is some combinatorics inside. And the degree is the top Chern class of this bundle. Okay, now before give the combinatorics, I want to show you this paper, which is nice. And it is shown here for a reason that more or less a few years after, Aluffi and Harris solved the same problem. And in a more general setting, they gave a topological formula to compute the ED degree. And that is interesting because now there is an assumption of X which is smooth, but no assumption of Q, so no transversal. So in some sense is better than Catanese triform because you can use for any Q. And after they found that they computed for the Segre case, and Aluffi sent me an email. I found this formula is the generating function completely different from ours. Wow. Then we check at particular cases, always the two formula coincided. So they should be the same, but we have not a proof that they are the same. Probably can be done, but I'm pretty sure that that's interesting. For different formula that are the same, but the only proof pass through complex singular tuples and ED degree. Let's comment here. This is topological Euler characteristic. And there is another way to write down these four terms, which is chi of X minus the union. Topological Euler characteristic is a game that behave additively on varieties. So if a variety is the union of two, you can compute as the chi of the first, the chi of the second, minus the chi of the intersection. Like if you count something, is like a counting function. And indeed, if you apply here, you get exactly this result. Among these four terms, the most difficult is the last one. In many cases, these three are known, and all the difficulties here.
So H is any hyperplane?
H is any hyperplane, general. Oh, sorry, it's not. H is general hyperplane, and Q is your favorite distance function. So it's beautiful, and makes transparent the dependency on the quadratic form chosen. Oh, I did a disaster, sorry. The battery. Corollary, the formula of ED degree works for any SO invariant The reason is that Q is the same as isotropic vectors. Now I don't show the details. I don't know a proof without a Luffy-Harris. Okay, here is written. Because this expression, when V is equal to above V, when you get the symmetrization, the quadratic collapses always to them. So does not depend on I. And then Q is the same and you get the same. Okay, this is the interpretation of Zeiberger. They put this generating function, HM, you get this number of critical points obtained, and he proves. And it's nice because there is an analogy with the generating function of the hyperdeterminant, and a consequence is that from here you can prove how they behave, for example, for tensor cubic when n goes to infinity, and you see it's pretty nice, this expression because appear pi, which is funny, and this was found by Antoni. You see this number is now exponential. And in the symmetric case, you get a simpler formula. This was found first by Fornes-Sibony and reproved later by Parbright and Sturfels. You fix a symmetric tensor, now depends on two numbers, degree D, homogeneous polynomial of degree D, and n+1 variables. This is the formula. Note that the denominator divides the numerator, so it is simply a polynomial, and if you compute for d equal to, it is just a sum of 1 m times, and this number collapses to m. So this is nothing else than the degree of the Veronese embedding with respect to the Bombieri-Weil product. Our interpretation with the Friedland show again this is a Topchan class, so it's a different proof of a very simple bundle. The quotient bundle twisted by d-1. You compute the Topchan class and comes this number. Okay, this is a beautiful theorem by Li Kun-chi. It's maybe the only case beyond matrices where I know an explicit formula for the AD polynomial. Is the case when you compute the distance from the discriminant hypersurface for polynomial of even degree, and you see it factors in this way. This is the discriminant of what? Of f minus a multiple of your favorite quadric, which defines the metric on V at power d half. D is even, and so you can, this is a quadric, so the degree is d, and they separate. So this means that's that if you want to understand the poly, you can do the following: you pick your x, and then you on the screen x. Let's call v of f. You do f plus dq d half. Then you find a moving family with respect to t. And in some point, you find a singularity. These are exactly the values of t that gives the offset from your f to here. So you can visualize how many there are, where there are. And I remember I had animation of these when you have a quartic curve, you modify and you find all the possible singular. In this case, if I'm not wrong, they are exactly 13. You have, or 14 maybe, you have 14 singular quadrics obtained as the discriminant of this, so when the pencil is vanishes. So at best of my knowledge, there are no generalization in odd degree and in the non-symmetric case, which is pretty mysterious. The mysterious fact is that why this works so well and that there are no generalization. So in some sense it makes this as a generalization of the characteristic polynomial of so you have the characteristic polynomial of a quadric. This is the identity now, it's this one, and in general for NRF, this is the analog of characteristic polynomial of a hypersurface of even degree. Okay, it's
So this is the LED polynomial of the Veronese. Right?
exactly
Also by
for even degree. Yes.
for even degree.
Yes. Yes. So now, just a small remark about number 2, 4. I told you at the beginning we can count the real critical points. Then the space of tensor, when you start from a real, is divided in chamber according to the number of real eigenvalues, and you can make the average. So count the volume of each chamber with the distribution, and you fix the Gaussian one. And this is the result we found. So for this is for binary forms. So the Cn means the Veronese of P1 of degree n, the ED degree is n, and the average is this number. This is a bit larger than square root of n. There is this factor here. For the twisted cubic, we have a square root of 7, which is a bit less than 3. And these are the last results that were obtained in his thesis by Luca Sodomaco some years ago. I remember the discussion was just when COVID was, when the pandemic was arriving, and this is still in our remember that if you have a transversality, which is a general assumption, then the ED polynomial has a nice behavior in the sense what is new, that Pi is homogeneous exactly of the complementary degree to T. So in particular, the leading coefficient has degree 0, and then is constant, and so the ED polynomial is monic. So you can interpret it saying in the algebraic ring extension, the distance function is an integral element because it's a solution of a monic equation. And now, if you take the Veronese, the assumption is not satisfied. The polynomial is not monic, and Sodomaco computed in this ED. This is still unknown because, well, no, for even degree was the previous one, but this was also for odd degree. Computed the first and the last term. The first is the discriminant square, which is not a surprise. And the second one is more complicated. And it is the discriminant, not the discriminant, is the dual of the D Veronese embedding of the quadrant at some power. And as a corollary, you know that for matrices, the product of the eigenvalues is the determinant. So you can ask what is the product of eigenvalues? And the product of eigenvalues is given by the ratio between these two. Since there was a t-square, you see I had to put a square root. And it's a quite maybe not expected formula, no, that it is rational. We hope for some polynomial, but the degree did not match. And now they match with the number, which is given by the formula of Forness and Siboney. If you put it works perfectly. And the last slide gives an explanation of what we found by Cayley and Salmon. In transversality assumption, you start from x, and now the constant term, when it equals 0, is computed as g. What is g? It is the dual of this. And you remember when I show you the ED polynomial of an ellipse, there was the ellipse and there was the ellipse was here, and there was an extra term. And I told you, I will tell you at the end what the extra term is. There is no real points. The extra term is this one.
So X dual intersection.
With the Q and then again the dual.
Always has a non-degenerate overriding.
Yes.
I guess because the quadrant just moved that.
The only case is when X is contained in Q, which you have to avoid. But otherwise, it is non-degenerate. It's quite strange. The quadrats have a strange behavior with the dual.
Yeah.
And
basic property.
so it explains a bit this why we found such a thing. Okay, I stop here. Thanks.
You have the questions.
So maybe I have. So this result by Luca and you on product of eigenvalues, does it generalize to a product of singular values?
I think Luca did in the binary case.
In the binary
So 2, 2, 2, 2, 2, there is a formula. In general, it should be to be done. It's probably doable, but I think it's open. This was a question by Limliken, computed this product, and I think he was a bit disappointed by this ratio and was more complicated than what expected, I think, no, in the Veronese. And if it is so complicated in the Veronese, probably in the Segre case or Segre Veronese, it is quite technical to be written down. But it should be nice, of course, to found because what's the analogy? I did not tell that the hyperdeterminant vanish if and only if one critical value is 0. So there is the. So at the beginning you think, well, so the formula is the product there, no? The hyperdeterminant is no, because it is just the numerator. You have also a denominator.
In the matrix case, the Borgheri-Weil norm squared of a matrix is sum of squares of the eigenvalues, okay? Or singular values, if you're in non-symmetric case. So can you see that this can be possibly
No,
general.
I don't think so, because a consequence of what you are saying as sum of squares is that the discriminant of the characteristic polynomial of a symmetric matrix is a sum of squares. And then this is the reason
Yeah, why
the solution are always real, no? So you have only one chamber. But in the case when you have tensor and not matrices, when the devil put the hand and not, you have different chambers. And so cannot be a sum of squares.
maybe
There should be an hypersurface.
maybe you have to take on the real. Right?
No, okay, but sum of squares on the complex has a solutions, but over the real, also a solution, but in codimension bigger than one. That's the point, no? So, of course, if there are a reasonable simplification of the formula, maybe it could be hope. Yeah, there is always a hope to find some simplifications. It's fascinating. Passing from matrices to tensor is all this picture. I think we are just in the top of the iceberg, no? But a lot of things has to be understood.
Okay. No question? If not, we can again.